So what we're looking at here is how to solve a complex circuit where you have something that's in parallel and something else, another resistor that happens before that. So you can't just solve it in series, you can't just solve it in parallel, you have to use a combination of both of them. So in here, I will be color coding things as we go along. Anything that's blue is voltage, purple is current, green is resistance, and P is power. And that's the same colors that I try and use on the board in class. In this specific setup, we have a 9-volt battery. We've got 36 ohms and 18 ohms in our parallel component, and we have 3 ohms for the other resistor that we have. And so the first thing we have to figure out is just what's happening. And if we took, and instead of having a parallel component here, we put this in, and we had a parallel, or we had a different component here for our series, we would be able to calculate our 3 ohms plus that and be able to get our total resistance. And then we'd be able to solve several different things out of there. And so the first thing that we have to do is figure out the total resistance of the parallel component, so then we can treat it as something in series with the 3 ohm resistor. So in order to do that, we know that in a parallel component, the total resistance is equal to 1 over each of the other resistances. And in this case, we have 1 over 18 ohms plus 1 over 36 ohms. And when we do that, we get 0.083 repeating, and it just keeps on going. That's not our final answer. That's still equal to 1 over our total resistance for the parallel component. So in order to get the RT of the parallel component, we have 1 over 0.083 repeating. And if you're doing this in your calculator and you have this answer, to get this one, just take 1 divided by answer. And when you do that, you'll get that that parallel component is equal to 12 ohms. So what that means for us in our calculating is instead of having all this there for this part, we can move this and say, oh, I've just got a series circuit where I have 3 ohms and 12 ohms, and then it goes back to the battery. That allows us to do the second part, the total resistance of the circuit. So we know that our total resistance is just by adding up R1 plus R2. In this case, that's all we have. So we'll take the 3 ohms. The current comes out of the battery. It goes through the 3 ohm one. It goes through the parallel component, and the parallel component is worth 12 ohms. So we'll say plus 12 ohms, and that leaves us with an RT of 15 ohms. The difference here is that this total resistance is just for the parallel component, and this is for the whole circuit, for the whole thing. Now, we know this resistance for the whole thing. That's if we take this setup that we have and we touch it to the battery, we've got this resistance. Well, that resistance and that voltage can allow us to be able to figure out our current. We know for current that we have I equals V over R. We'll use our RT here, our total current for the circuit. And so we'll take our voltage of 9 volts divided by our 15 ohms. And when we do that, we get that we have 0.6 amps equals our current. So what that shows us here is that we have 0.6 amps coming out of the battery. When we get over to this spot here, we've got 0.6 amps going through this resistor, and it goes into the box and it comes back out of the box and goes back into the battery at 0.6 amps. Going back in there. We'll get to what's happening in the box, but right now that going in we've got 0.6 and coming out we've got 0.6. The next thing that we'll do then is to get the voltage drop for each component. Now we know the current that's going through our 3 ohm resistor, and we know the current going through the box. We don't know how it's split, but we know it's there. And so we're going to calculate our voltages. Well, we know that V equals IR. And so for the 3 ohm resistor, we know that the current is 0.6 amps, and our resistance is 3 ohms. 0.6 times 3 gives us 1.8 volts. That means that in this resistor, we've got a voltage drop of 1.8 volts. Now there's two ways that you can find the voltage drop here. You can say, well, I've got 9 volts to start, and I drop 1.8 here, so minus 1.8, and I end up with 7.2 volts. That would say that I have, in this resistor, I have 7.2 volts there. The other way of doing that is to do the exact same thing that you did here and say V equals IR. You've got 0.6 amps going into and out of the box, and the box itself is equal to 12 ohms. And when you take 0.6 times 12, you also end up with 7.2 volts that get dropped there. I don't have a preference on which one you use. Just show your work. So 9 volts start here, goes around. I've got 1.8 volts that are used up here, 7.2 volts that are used up there. By the time I get back, I can't have any left. 7 plus 2 plus 1.8 gives me 9. Now we open up the box. We still know in parallel, we still know that we have a drop of 7.2 volts in there. And that means it doesn't matter which path, whether it's this path or that path, because once the current splits, it only touches the path and the resistor that's on the path that it goes on. So if I follow the current out of the battery here, and I go up, I lose some of my voltage here, I lose 1.8 volts here, and then if I go up here, I lose 7.2 volts and then go back. If I go down here, again 7.2 volts and go back. So when I calculate the current for each path here, well, now I'm able to figure out some various things with that. So I know that I equals V over R. And so for the 18 ohm resistor, I have 7.2 volts. For both of them, I have that over my 18 ohms. And when I do that, 7.2 divided by 18, I get 0.4 amps. So if I follow my current up here, and I go up here, coming across that way, I've got 0.4 amps. That'll go back and get back in line here and go back down to the battery. If I take and I do that here, and I say I equals V over R, parallel component, so it's also 7.2 volts that will be dropped there. And this time I have 36 ohms for my resistance. And when I do that, I end up with 0.2 amps. So, well, I've got 0.4 amps going up here. Come down here, I've got 0.2 amps that go down there. Again, go back and join up with everything. If I look and I have my 0.4 and my 0.2, that equals my 0.6 that come out of the battery and go in. The only place that it splits is on those two paths. The last thing you need to do is to solve for the power on each resistor. Now the equation for that is not anything that's too crazy. The equation for that is just P equals IV. The difficult part is that at this point you have a whole lot of information to figure out what's happening. So if I go over to the 3 ohm resistor, I know that I have a current of 0.6 amps and a voltage of 1.8 volts. So I'll say current of 0.6 amps times a voltage of 1.8 volts. And when I multiply those, I end up with 1.08 watts in the 3 ohm resistor. Oops, you probably want to see that. If I do the same thing here and I say power equals, in the 18 ohm resistor, I have 0.4 amps and I have a voltage drop of 7.2 volts. So I have my 0.4 amps and I know that I've got 7.2 volts. So I'll say 0.4 amps times 7.2 volts. And when I do that, I get 2.88 watts in the 18 ohm resistor. Lastly, I'll do that again. This time I'm going through the 36 ohm resistor, and I've got 0.2 amps, still 7.2 volts. So I'll say 0.2 amps, 7.2 volts. When I do that, I get 1.44 watts in the 36 ohm resistor. And so in every situation, you're walking through a process that's similar to this, where you're figuring out what's happening in your parallel component in the way of resistance. And to do that, you follow your resistance equation. In this case, we ended up with 12 ohms. And you use that in conjunction with the other resistors that are then in series. I took the 12 ohms and the 3 ohms and added them together. Got 15 ohms for the whole circuit. For that circuit, you want the current, so 9 volts divided by 15 ohms gives you 0.6 amps. And that's coming out of the battery, going back into the battery. Yes, it splits here, but for the most part, in the rest of it, it stays the same. And using that, you find the voltage. So V equals IR, so you have your 0.6 amps times your resistance. You get 1.8 volts here. You can find the other one by subtraction, taking your total voltage minus what you just lost here. Or you can do it by using V equals IR, with the total current, and then your resistance for the parallel component, the calculation on that. In this case, that was 12 ohms, so it gave us 7.2 volts. Either way, they end up being the same. They should. Once you have that, once you know that voltage drop in here, then you can calculate your currents across each path. The current splits, and so you have I equals V over R, so 7.2 over 18, 7.2 over 36, and you ended up with 0.4 and 0.2 amps. 0.4 plus 0.2 adds up to equal 0.6 that we have up here. Lastly, once you have everything, you can go through and get your powers. The biggest thing about this is making sure that you're using the right current and the right voltage in each situation. And so in this case, we did, each one of those from what we had, and then got the powers that we have. You should get, if you haven't received one of these yet, make sure you talk to me about it, a little paper like that walks through those 6 steps. And you can stick that into your notebook so you have it available to you.